Good morning, students. Today we are going to discuss basic laws related to magnetic field, that is the lecture 2 of unit 3. So in today's lecture we will discuss some basic laws related to magnetic field which you have already studied in 12th class, but we will revise here because it is in your syllabus. So Ampere's circuital law is the first law which states that line integral of a magnetic field intensity around a closed path is equals to the total current enclosed by that path. So here is the formula. Closed integral h dot dl is equals to summation of I. Here's the summation sign is showing that there is a total current. A closed integral is the sign is showing here along with integral sign by a circle. So if we are considering a current carrying element which is having current I and the magnetic field intensity h at a distance r from the conductor is given by closed integral h dot dl is equals to I. dl can be, if we'll consider the circumference of the conductor, then we are having the periphery like 2 pi r. The length of that conductor in a circular form should be written as 2 pi r, and the h into 2 pi r is equals to I, so h is equals to I by 2 pi r. If we are having n number of conductors, capital N number of conductors, then the current enclosed by the path would be h is equals to n into I upon 2 pi r. This is all about the Ampere's circuital law. Now comes to the second important law, that is Biot-Savart's law. So Biot-Savart's law, we already know that if we are having a current carrying conductor here and if we want to calculate the magnetic field intensity at a particular point P, then we can calculate it by using the Biot-Savart's law. What Biot-Savart's law says? According to Biot-Savart's law, the magnetic field at any point P due to an incremental element means this part of conductor, incremental element due to length dl carrying a current is directly proportional to, the length of element, that is dl. Number 2, current carried by the conductor, that is I. And 3, the sign of angle between the line joining P with the length dl, that means this point O and P. This line is joining O to P, and the angle difference between this elementary part, that is dl, the conductor length and this line, the angle between these two is known as the theta. So sine of angle theta between the line joining point P with the length dl and it is inversely proportional to the magnetic field strength is inversely proportional to the square of distance of this point from the element. This distance from O to P is r. The distance between O and P is r. So it is inversely proportional to the square of r. Hence the field strength is given by, we can write it like dH is directly proportional to I dl sine theta by r square. And when we putting here the equal to sign, then the proportionality constant would be 1 upon 4 pi. So the formula is now dH is equals to 1 upon 4 pi I dl sine theta by r square, when 1 upon 4 pi is the constant of proportionality. And the Biot-Savart law is very helpful in calculating the field strength H due to a particular configuration for a current carrying conductor. Now comes to the next law, that is force on a current in a magnetic field. It is basically a formula which is widely used in the application of or working of the electrical motors. So if we are having a conductor carrying a current I is placed in a uniform magnetic field, as we show that lines are showing uniform magnetic field here, and this is the conductor carrying current I, and the angle between the magnetic field and the current carrying conductor is known as theta. So the current carrying conductor is in a uniform magnetic field of flux density B, is experiencing a magnetic force, and that magnetic force is directly proportional to the current flowing to the conductor I, the length of conductor small l, flux density of the uniform magnetic field, that is capital B, and the sign of angle between the conductor, that is theta. So F is equals to BIL sine theta. This is the formula for the force on a current carrying conductor, and the direction of this force can be calculated or determined by the applying flaming left hand rule, as we are having a diagram here of left hand. So this is forefinger, this is middle finger, and this is thumb. If we stretch our hand in in right angle to each other. Like if we are placing our hand like this, so as you can see, this thumb and the middle finger and the forefinger, these are having exactly 90 degree to each other mutually, as we can say. As this diagram is 2D, so we can see this current and field are having 90 degree angle difference, and the motion is, because it is 2D, it is placed here, but we can write it like this. We can understand it like this. The direction of pen is showing the direction of motion. Then we are having the difference between the current and this motion, and the angle is 90 degree. And again the field and the angle between this motion is 90 degree, and these two are having a difference of 90 degree already. So the thumb is indicating the direction of force, and the forefinger is indicating the direction of field, and the middle finger is showing the direction of current. Now comes to the next part, that is BH curve and his magnetic hysteresis we will discuss. So BH curve is the curve drawn between magnetic flux density B and magnetizing force H, is known as BH curve. It is different for different magnetic material. So here is the graph. Here on y-axis we are having flux density, and on x-axis we are having magnetizing force. Here is the pattern, typical pattern. It is having 4 clear distinct parts: 0 to A to B, B to C, and further beyond C. So it in OA region, the increase of flux density is very small and it is almost linear, and in AB the flux density increases almost linearly, more linearly towards the towards B point, and in BC again the increment in magnetic field intensity is very small, and after C the saturation comes, and the curve turned out to be flat or constant. So the flat part of curve corresponds to the magnetic saturation of the material, and non-linearity, that this curve, as you can see, is not completely linear. So the non-linearity of the curve indicates that the relative permeability mu r of a magnetic material is not constant, but it depends upon B. So the curve is of different shapes for different materials, and in next lecture we will discuss magnetic hysteresis and comparison between electric field and magnetic field. I hope you will study it and you have understand. If you have any doubts you can ask me, and make this notes in your copy. I have already sent you the soft copy, so learn it properly, remember it, and ask if there are any questions. Thank you.